Welcome everyone, thank you very much for coming. I love talking about my research, so I'm really pleased that so many people have come along to give me a chance to talk about my research side of my job here at the University of Canterbury. To start, it's a summary a bit of my research and what I'm going to talk about tonight. So I call myself an astroparticle physicist, which means that I do research in both astronomy and particle physics. What I basically do is explore the universe using a particle called the neutrino, and that's what I'm going to tell you about tonight. And through detecting neutrinos, we can learn about objects out in the universe, astrophysical objects, and we can also learn about theories of particle interaction. The research I'm going to talk to you about was awarded the Physics World Breakthrough of the Year in 2013, so it was, for at least 2013, seemed to be the biggest breakthrough in physics for that year, and that we detected astrophysical neutrinos. So I'm going to tell you about that. Just first going to just take a little pause and just think, what is physics about? So we, as physicists, we want to really explain everything. That's our goal. So we want to explain phenomena from atmospheric physics to magnets, electrical discharge, quantum phenomena. We want to be able to explain those just to understand what's happening when we see those kind of phenomena. And for us to understand means usually writing down some kind of mathematical theory behind what's happening. And then when we can understand it, we can develop tools that use it, innovation based on it. But my research is really on the understanding level and trying to understand some phenomena. In particular, I'm really working in particle physics. So I'm going to talk a little bit first now about particle physics. So particle physics is kind of the extension of when we talked about the Greeks and who were thinking about atoms, and they wanted to divide down matter into what was the basic building blocks of matter, which they called the atoms. And that's what we are trying to do as particle physicists, understand what are the basic building blocks of matter, what is the most fundamental particles that you can't break down any further, and what are their interactions. So that's what particle physicists want to do. So sort of to orientate that a little bit, there's this schematic here showing firstly a crystal, which shows something about its size, and then a crystal is made up of molecules. So we go down a size crystal made up of molecules. Molecules are made up of atoms. So here is some kind of schematic view of an atom. And the centre of the atom, this little dot's meant to represent the centre of the atom, there is a nucleus. So it was Rutherford who told us about this. It was a nucleus at the centre of an atom. And it's showing these little kind of ring things. They're indicating electrons, which are really some kind of quantum cloud around this nucleus. So here, electrons are fundamental particles, we believe. So this come down here as a fundamental particle. But the nucleus is not fundamental. It is made up of neutrons and protons. So now, next stage down, we're talking about a proton. And then protons, we now know, are not fundamental either, and they're made up of these things called quarks. So now we believe these are the fundamental particles that we're made up of. So basically, we're made up of electrons and quarks. That's as fundamental for us. A neutrino is on the level here, and I'll talk a little bit more about neutrinos. I just want to talk a bit more about particle physics. Does anyone know what this picture up here is about? What it is? Does it recognise anything? So it's CERN, home of the LHC, the Large Hadron Collider. So up the top, it's a kind of artist type picture. So we can see from the outsides around Geneva, and the red ring is indicating where the CERN tunnel is underground. And then here we're getting a view of the CERN tunnel where the protons are first they're accelerated and then collided within these tunnels. So the idea at CERN and in the LHC is to accelerate particles, protons, particularly to really high energies, smash them together and see what happens. So they're trying to see if there's some more particles, new particles that we don't know about, created. So that's one thing. They're trying to study the interactions of the particles we do know about, like the quarks, at those really high energies. So we're trying to accelerate particles to extremely high energies and understand what the physics is of particles at really high energies. So that's kind of the goal of CERN. And my goals from my research is really similar, but I'm using accelerators out in space. So the same kind of physics we're trying to do here, except instead of using man-made accelerators, I'm thinking about studying accelerators that nature has provided out in space. And we know that there are astrophysical accelerators that produce particles with at least 1 million times more energy than anything we've produced at the LHC, at the Large Hadron Collider, and will ever produce. If we wanted to try to reach these kind of energies that nature has accelerated particles to, we'd have to build an accelerator much bigger than the Earth. So we're not going to be able to do that. So to go to those really high energies, we have to use the particles that nature has provided and study those accelerators out in space. Trouble is we don't actually know at the moment where nature is accelerating those particles. So how do we know? We do detect the particles. We call them generically cosmic rays. So cosmic rays, they're charged particles, mostly protons, and if you see, if you're lucky enough to see an aurora, you're seeing actually cosmic rays. Those charged particles are produced mostly by the sun. So there is a range of energy of charged particles, and the particles themselves, they usually interact in our atmosphere. And that's actually really lucky for us as humans, because we'd be well irradiated by now if our atmosphere wasn't protecting us from the cosmic rays. So they interact in the atmosphere, but higher up in the atmosphere there's more cosmic rays, and it's when pilots have to monitor how much flying they're doing, because they're getting a higher radiation dose being higher up in the atmosphere where the cosmic rays are coming in. So the cosmic rays, and this is what this picture is showing, a cosmic ray interacting in our atmosphere and producing other particles which are detected by other detectors that I don't work on, but cosmic ray detectors. And from the particles that are detected here on ground, you can work out the energies of these cosmic rays that are coming in. And that's how we know that there are particles entering our atmosphere with well over 1 million times more energy than those produced in the LHC. So very high energy particles produced. I'll show you a graph, a little wary of showing graphs in a public talk, but I'll talk a little bit why I want to show you this here and what it's telling us. So on this axis is energy, and this axis is number of cosmic rays. So what I want to show you is that we see cosmic rays over a wide range of energies, and there's lots and lots of them at low energies and not so many of them at very high energies. And the lots of them at the low energies are coming from the sun, principally. Then this shows it's dropping down. One thing is that this is a very kind of straight line, and so it suggests that the similar kinds of processes are accelerating and producing these high energy particles over the range of energy. And here showing that there's about 1 particle per metre squared in this energy range, and we actually do think that we know where these ones are produced, and we think it's in the remnants of supernova in our own galaxy. But these highest energy ones, which are actually very rare, and here we don't know where they're produced. And the problem is that even though we can detect the particles come in and they produce those kind of showers that I said, you can still work out the direction of the incoming particle from those showers. But the trouble is that there are magnetic fields around us and around in our galaxy, and because these particles are charged particles are bent in magnetic fields. So even though we can tell the direction of the cosmic ray, the charged particle, as it comes into our atmosphere, that doesn't tell us anything about where it's actually come from, because it's come presumably from some kind of accelerator out in space, but it's followed some path like this because of the magnetic fields between us and wherever it's accelerated. So even though we tell where it comes into our atmosphere, that doesn't tell us where it's actually come from. So I want to study these accelerators, and I know they're out there because of the cosmic rays that have been detected, but just detecting the cosmic rays doesn't actually tell me where they are. So I'm going to tell you that that's the reason, that's why I wanted to detect neutrinos. First, I'll just tell you a little bit more about neutrinos. So as I mentioned, there are quarks and electrons are the fundamental particles that we're made of. Actually, your body produces around 350, I think, million neutrinos per day as well. They just stream out. That's because we've got some potassium-40 in our body, and that decays radioactively and produces neutrinos. So you are a neutrino producer. So those neutrinos are just low energy and not the ones that I'm not interested in detecting your neutrinos. I'm interested in detecting much higher energy neutrinos. So I want to tell you a little bit about neutrinos and why I want to detect them. But first we just kind of have to understand a little bit about the properties of neutrinos. So I said fundamental particles that you may or may not have heard of, but at least somewhere in this line you've probably heard of things, are electrons and quarks. And neutrinos are at that level, but they're, in a particle physics theory sense, they're very similar to an electron. But the big difference is that they are neutral. They have no electric charge. So they are something like an electron, but with no charge and a very small mass. And so this means that they are very weakly interacting. So as I said, they're produced in radioactive decays in our own body. They're produced in the sun in the same nuclear fusion reactions which produce light, produce photons, produce the energy from the sun, produces many neutrinos. So when we see the light from the sun, it's taken around 300,000 years to get out from the centre of the sun where it was produced in the interactions. Then it takes 8 minutes from the surface of the sun to reach us, as it's 8 light minutes from between Earth and the sun. But it took 300,000 years for that light to get out. So if the sun stopped producing energy now, we wouldn't actually know for 300,000 years because the light's still coming out. But we would know because the neutrinos that we detect from the sun would stop straight away. Because the neutrinos just stream straight out from the centre of the sun. And there's this 100 billion neutrinos pass through your thumb. And actually any square centimetre on your body, your thumb's not special, any square centimetre on your body, 100 billion neutrinos will pass through every second. And they pass through whether it's night or day. So now the sun's set, probably nearly over there somewhere, but you are still receiving neutrinos even though you can't see the sun anymore. So neutrinos are extremely weakly interacting, and that's basically because they have no charge. So they don't interact by electromagnetic force. They don't interact electrically because that relies on the electric charge for things to interact electrically, and they don't have any electric charge. So I said when we looked at this picture that here was a kind of schematic view of the atom. And if you can kind of see those numbers that you can't see particularly well, you can see that the nucleus is a factor of around 10,000 smaller than the atom itself. So if you're thinking about matter, the mass of an atom is contained in the nucleus. And that nucleus is 1/10,000th the size of the whole atom. So if we want to think about an atom with something like the size of this room, then the nucleus would be like about a grain of sand in the centre of the room. That's how big the nucleus would be, which is where all the guts of the atom is. And then the electric cloud around there is essentially nothing that's creating there, the volume. So you, me, and we're mostly empty space, because the nucleus at the centre is just a grain of sand and the rest is the empty space around us. So we're mostly empty space. Now we don't kind of feel like empty space and we don't look like empty space. And the reason for that is because light bounces off me. So I look solid. You can't see through me because light's bouncing off me. And I feel solid because the electrons in this table feels kind of solid, even though I'm telling you it's kind of empty space. It feels solid because the electrons in my hand don't like the electrons in here. And so the electrons in my hand won't let the electrons in the table pass through. So things feel solid basically because of the electrons within material. But I think for neutrinos don't care about electrons. So neutrinos just see the Earth as the empty space that it is if you didn't worry about electrons, if you just worried about the nucleus at the centre. So that's how neutrinos see the Earth, and that's why neutrinos just pass through, because they see the Earth as empty space and they see us as empty space. So just because they are neutral, essentially, and their only interaction that they don't go by, they don't care about electromagnetic interactions. They can just pass through and see the universe essentially as empty space. So that makes neutrinos really interesting cosmic messengers, because they can pass, as I said, they pass essentially straight out of the sun. So by monitoring neutrinos, we could see if the sun has stopped working, and I tell you it hasn't so far. We're still detecting lots of solar neutrinos, so we've got a good 300,000 years ahead of us for that. But it also means that we can look for neutrinos out in space. And I mentioned here neutrinos produced in radioactive decays and in a body in say, the centre of the sun. They're also produced in cosmic ray interactions. So when cosmic rays interact, they produce neutrinos. So these cosmic rays, these really high energy particles that are produced somewhere out in space, presumably close to where they are produced, sometimes they interact. So some of them, not all of them interact, because we detect them here on Earth, so they're leaving, but some of them, they're presumably produced in quite dense regions of the universe, and so some of them will interact near their source. And when cosmic rays interact, this little circle is telling you about it, but you don't need to worry. What you need to take out of this, this picture is that neutrinos are produced when cosmic rays interact. Also, light gamma rays, photons, are produced. And both the neutrinos and the gamma rays, that's what this thing is, gamma rays for high energy photons, high energy light, neutrinos, they're produced when these cosmic rays interact near their source. And they will pass, they aren't affected by magnetic fields and can so travel straight towards us. And so people look for gamma rays. The trouble with gamma rays is they interact very readily. And so they are absorbed by pretty much anything that will be in their way between the source and there, including something called the cosmic microwave background. And because of the cosmic microwave background, you cannot actually see much further. Well, in the highest energy gamma rays that we'd like to look at, you can't even really see outside beyond our galaxy, much beyond our galaxy, and really high energy gamma rays, because they're absorbed by the cosmic, they interact with the cosmic microwave background. So neutrinos are the only way for us to directly, with straight line view, observe the really high energy universe. So that's our goal, is to detect the neutrinos coming from these astrophysical objects, identify these regions in space that are accelerating particles way more energy, to way more energies than we can do on Earth, and then the same kind of physics and the same kind of understanding that we want to learn through at CERN, so probing particles at their highest energies, we want to be able to do in those high energy regions. So first is we want to be able to detect the neutrinos from them. So astronomy is seeing cosmic messengers, and we can look, we do astronomy in visible light and many other wavelengths of light, like radio, infrared, X-rays, gamma rays, and they all give us different views of the universe, and we learn different things. They show us different energy processes by looking at the different energies that lights are produced in the universe. And so neutrinos are another view, at the highest energy view, that we can see the universe with. The advantages for neutrino astronomy, as I mentioned, that neutrinos, because they are so weakly interacting, they're not attenuated by nearly anything, and their path is not affected by magnetic fields, so they will travel straight. And when we see neutrinos, it will tell us that particular kinds of processes, the ones that produce cosmic rays, are happening in those in objects. So they're a direct messenger to tell us that cosmic rays are interacting and that are being produced at the sources. We have done astrophysical observations of neutrinos for a while. We've seen the sun, and also a supernova that was in, not in our galaxy, but one of the satellite galaxies, was observed in neutrinos in 1987, supernova 987A, which was just for about 10 seconds we saw the neutrinos. And until a couple of years ago, those were the only astrophysical neutrinos that have been detected. What we're wanting to observe is the origin of these ultra high energy cosmic rays, as I've talked about, and also then the suspects for where these might be produced, or what we already know are the high energy objects in the universe, because we can see gamma rays, not as high energy as we're talking about, but we have seen gamma rays from objects like active galactic nuclei, which are galaxies which have an active centre, which means they have a supermassive black hole in their centre, which is accreting matter, and as the matter comes in, it forms an accretion disk around it, and there are magnetic fields that are swirled there, and we know that there is high energy process happening there because we have seen gamma rays produced from there, but not, as I said, at the high energies that we've seen the cosmic rays at. And we couldn't see the gamma rays anyway at that high energy because they are attenuated. But so that's a place that we do suspect that could produce these cosmic rays. So that's one place that we're definitely looking for the neutrinos to be coming from. Similarly, gamma ray bursts. These are great bursts of gamma rays that are seen just for about the order of a minute. These go off, and in that minute about as much energy is released as the sun will release in its entire lifetime is just released in around a minute. And these observed, it's not completely agreed what they are. There seems to be two different types of gamma ray bursts actually, and one is probably something like a supernova, so a collapse of a very massive object, and the other type is actually believed to be two neutron stars or black holes colliding, and that's where what's forming the gamma ray burst. And as the gamma rays are produced, but we don't know if that's a place where cosmic rays are accelerated, so we're looking for neutrinos from there. We also look for dark matter, which is this mysterious matter that's observed by its gravitational effect, but not observed any other way. Dark matter interactions, or if dark matter gets together and does annihilate, it's called, then neutrinos should be produced. Well, many particles be produced, but only neutrinos will be able to reach us from many. So those are the kind of things that we're looking for neutrinos from. So we want to detect neutrinos. Because they interact so weakly, so hopefully I've motivated why I would like to look for neutrinos. Now I'm going to tell you about how we do detect them with a detector that is run by a huge, large international collaboration and was funded by the US, cost around $280 million US to construct. So I don't know if I've motivated you with $280 million worth yet. That's what the detector that we have built to see, and we now have seen these astrophysical neutrinos. And so, as I said, the neutrinos interact so very weakly, which is what makes them a unique messenger. It means that we can see them basically from the edges of the universe, but it does make them very difficult to detect, because, as I said, there's hundreds and hundreds of billions of them streaming through your body, and you haven't noticed, I don't think, that these neutrinos are streaming through your body. And so I want to actually detect them. So every now and then a neutrino will interact, because, as I said, for the atom with the little grain of sand in the centre of this room, every now and then the neutrino will hit that grain of sand. So it's a small probability, but it does happen rarely, but it does happen. So if we put a big enough target in front of the neutrinos, then we have a chance of seeing those interactions. So we don't see a neutrino unless it interacts. So we can't, just streaming through us, nothing. They don't produce anything as they stream through us. We have to wait for them to interact to see them. So we need to put a huge target in front of the neutrinos and monitor that huge target. And we use Antarctic ice as our target. So when a neutrino interacts, it produces charged particles, and those charged particles produce light, and that's what we look for. So this is a schematic picture showing this is where all our computing equipment and everything are on the surface of the ice at the South Pole, and our instrument, which I'll tell you about, is below the surface of the ice, so that we can use the big volume of ice below there, which is extremely clear, as a target for the neutrinos to interact. So this is a picture of one of our events, but I'll explain to you that's not what it looks like. That's a computer generated image of our events. The charged particles that are produced when a neutrino interacts produce light, and we look for that light. There are other neutrino detectors that have been doing this for many years. So as I said, we've been looking we've seen a supernova before, and we've been monitoring the sun for quite a while with neutrino detectors. We don't actually detect solar neutrinos with IceCube. So there are other detectors that do that. For example, there's one called Super Kamiokande in Japan and another one called Snow or Sudbury Neutrino Observatory in Canada, and they use big tanks of water. We use the ice, they use big tanks of water. And here you can see in this picture there's a little rubber raft with some people in it. You can't really see it because the resolution's not very good, but that kind of gives you an idea of the size of this big tank of water, because those are people there, and all around the big tank of water are light detectors. They're photomultiplier tubes. So it's the same principle. There's a big tank of water, neutrinos will interact in them, produce light, and with these light detectors around the outside of the tank of water, you can detect that light, and from that figure out things about the neutrino. Same kind of idea for the one in Sudbury. So these are huge big tanks of water, as you can see from this little raft there. Our detector is huger. So here is beside Aoraki, Mount Cook, and I've just done this roughly, but tried to give you a sense of scale. So here is our detector. It's roughly instrumenting about a cubic kilometre of ice. So here's the surface. Our detector is between 1.5 kilometres and 2.5 kilometres below the surface. But this is just to show you roughly around the volume of ice that we're instrumenting, something like the kind of peak or volume that you can see of Aoraki Mount Cook when you're there. So that's the size. And compared to those other neutrino detectors that I told you about, that's something like how huge we are. And the reason we are huge like that is because solar neutrinos are plentiful, so they can be that kind of size and detect solar neutrinos. The neutrinos that we're after are much rarer. So we're looking for a rare interaction of something quite rare. So we need to have a huge detector in place to do that. Here then I'll tell you a little bit more about our detector. So as I said, it's at the South Pole. If you're at the surface, this is what you see, our laboratory, which is where we collect the data. Below the surface are where our optical modules are. So they're basically just light detectors. And we have around 86, we call them strings, they're cables that have been deployed under the ice. And so how do we get them there? We have to actually melt a hole. So the holes are kind of around about that sort of diameter, and as I said, they go down to 2.5 kilometres deep. We go basically as low as we can. The ice is clearer down here. We tried at first actually a bit higher up, and the ice still had air bubbles in it which scattered the light and meant that we couldn't basically figure out the direction that the neutrinos were coming from very well. So we needed to go down to the clearest ice. Of course, when we're melting this hole, what we have is a hot water drill, a big hose with hot water drill, and we're pumping that water down into the ice, and it just melts this hole, and it's circulated round. It takes around 2 to 3 days to melt each hole down to 2.5 kilometres. We definitely don't want to hit the bottom, because if we do, we'll get some dirt, and that will go up into our hole, and then it won't be so clear. This ice here is the clearest and purest water that's actually known on Earth. So people try to make very pure water, and they haven't made it as pure as that water is there. So it's very clear. We have little LEDs on each of our modules that we can flash, and they're just little LEDs. We can flash them here and see them on the other side of the detector, a kilometre away. So that's how clear the ice is. So we have each of these cables, 86 of them, so we drilled 86 of these holes. It took around 5 seasons. You could only do it in the summer because, of course, it's dark in Antarctica for half the year, so we could only do the drilling over the summer period. So it took 5 seasons to deploy the detector, but we could use the subsets of the detector each year after that. So the detector grew and grew, and we could use the smaller size ones as we went. So they're about 125 metres spacing in this direction, and then on each of these cables we have 60 of our modules. You can see here, looking down the hole, the first part of the hole is actually dry. It's a real hole, and then after that it's just like a pool. of the water. And then see the cables, just lower them down and gravity takes them straight down. After we've melted the hole, have around a sort of 24 to maybe 48 hours for the cable to go down, and after that the ice starts to freeze in little fissures, and you can catch the cable on it and risk damaging the equipment. So you have to do it quickly. It actually takes a good 3 months right at the bottom for the ice to completely refreeze again, because ice is a very good insulator, and so for it to be really frozen in at the bottom takes around 3 months. And then once the modules are frozen and we can't get them out, they're there for good. And so see, we have 86 of these, as I've said, spaced around 125 metres horizontally, and then on each cable there's 60 of the light detectors. They're about 17 metres apart, so this is kind of schematic showing what it looks like on each of them. So we now have this cubic kilometre of very clear ice monitored with light detectors waiting for neutrinos to interact and the charged particles they produce to produce light. If you could go down under the ice, this is what it would kind of look like. You can't, but that's what it would. And then the idea is that a neutrino comes along. There's actually different types of neutrinos, so it doesn't matter too much. And neutrino comes along and interacts and can produce a very long range charged particle that can travel actually kilometres. So the neutrino interacts, produces this long-range charged particle that travels through the ice and produces light, and we track that light. So I show a kind of animation here. So that was a neutrino interacting, and the charged particle travelling through the detector and producing light. So the coloured bits on here, that's not what it looks like. They don't suddenly light up in colours. Our light detectors, they detect light, and they've got computer chips there, and then they send the message up to the surface. The colour here is to visualise, so they use the red through to blue to demonstrate timing, so that these were the first modules to be hit here, and then the size is how much light they were produced. So that's what we record then, is how much light and the timing of the light produced on all of, or detected on all of these. And as you can see from that, we can then figure out what direction the particle passed through. So here is an actual event. So the blue and the red lines are the reconstructions that we did of the particle. I'll do it again, maybe. So that was a real event, and the information that's contained in the colours and the sizes is what we get, and from that we've written computer programs to figure out the direction that the charged particle must be going, and that charged particle is very close to the neutrino's direction, so then we can work out the neutrino's direction from that. If that was all there was to it, what would have happened, we would have detected the neutrinos really easily and very quickly. The problem, and why we have lots of PhD students to help us, is we have something called backgrounds, which means that we don't just detect the neutrinos that we want to, we detect other things as well. So that's the tricky part of it all. Well, it's kind of tricky to build the detector, put the detector there. But the neutrinos interacting in them, that's fine, but we also detect backgrounds. They're actually from the cosmic rays that we're trying to study and learn about. So as I said, the kind of central aim for IceCube is to answer where cosmic rays come from. And so we want to detect the neutrinos that are created by cosmic rays when they interact close to their source. But I also mentioned that cosmic rays interact in our atmosphere, and that's how we can detect about the cosmic rays. It's lucky they interact in the atmosphere, otherwise we'd be radiated. But when they interact in the atmosphere, they also produce neutrinos, and they also produce the same kind of charged particles that neutrinos produce when they interact. So those cosmic rays that are interacting above the ice at Antarctica produce other particles that we will detect in IceCube. And so here is a little animation showing what well, I think it's Chicago somewhere, so not the South Pole, but it's showing a cosmic ray coming into the atmosphere and all the particles that are produced when a cosmic ray comes into the atmosphere. So many of those particles don't penetrate down very far, which is why it's good when we're a kilometre under the ice. But some of those charged particles do penetrate down into our detector, and we detect them. In fact, we detect around 3,000 a second of those muons, they're called, that are produced by cosmic rays. So our detector is flat out detecting things. 3,000 events are detected every second, but they're all not really what we're looking for. They're just the products of cosmic rays interacting in the atmosphere. And they also, the cosmic rays interacting, produce neutrinos, atmospheric neutrinos we call them, because they're produced in the atmosphere, and we detect those as well, and we do study them. They're interesting, but they're not those astrophysical neutrinos that we want to see. So to get to the astrophysical neutrinos that we want to see, we have to collect all of this data that we get and reject or get rid of it somehow, or figure out which ones are the needles in the haystack and are the astrophysical neutrinos that we want. So 1 in a million gets us down to atmospheric neutrinos, and then we have to go further to get to the astrophysical neutrinos. So a needle in a haystack problem is actually really easy if you have a magnet. And so for us, the magnet part, the clever part, is lots of PhD students to figure out how to take away or eliminate the background and give us the astrophysical neutrinos. The kinds of things we can do is we can look for things going up through our detector. So these cosmic rays interact, they produce these charged particles, but they're always going down. So cosmic rays do interact over London somewhere, and they produce the same, but those charged particles get absorbed by the Earth. The neutrinos they produce can come up through, and we will detect those neutrinos, atmospheric neutrinos. But anything that we see that's coming up through our detector is definitely from a neutrino. It could be an atmospheric neutrino or an astrophysical neutrino, but it's definitely a neutrino if it's going up through the detector. So that's what we do, is we look for upward going tracks. We also look for events that we say start in the detector. So when we see no light on the outer parts of the detector, but then light suddenly appears in the middle of the detector, we know that was a neutrino interacting there, because the charged particles produce light all the time and they're coming down. So we know if we see something start, light just appear in our detector and travel on, then that will be from a neutrino. And we can also just detect all these tracks and then look for hot spots that will tell us we're getting a lot of events from one direction, because the cosmic rays are uniform, so they don't have hot spots. So we would look then for hot spots and look for point sources. And we can also look, the same kind of ideas, we know where there are high energy astrophysical objects, and we can look for correlations in the events that we see in the direction of the astrophysical objects, and see if we see an excess of events, more events coming from the direction where we know there are astrophysical objects, which could tell us that what we're seeing is associated with those astrophysical objects. So that's the kind of ways that we look for astrophysical neutrinos. And so we've collected well over 100,000 neutrino events now with our detector since we first started deploying it. But until recently, all of those hundreds of thousands they were all definitely neutrinos. We're very confident neutrinos that we were seeing, but they were all consistent with just being atmospheric neutrinos. So neutrinos produced in our own atmosphere. So when I said cosmic ray that interacted somewhere over Europe and produced a neutrino, travelled up through the Earth and happened to interact in our detector, and we detected it then. So we have seen around 100,000 of those atmospheric neutrinos. Until recently, we couldn't say that any of those were astrophysical neutrinos. And now we have seen the astrophysical neutrinos, and that's what I'm wearing one on my t-shirt, and there was one on the cover of the Science magazine. And how can we tell that these particular ones are astrophysical neutrinos and not the atmospheric ones? Well, mostly it's from their energy. So here is my kind of second graph to try to tell you the crux of why I know that these are astrophysical neutrinos. So again, here is energy, something to do with energy on this axis, and the number of events on this axis. And what these black crosses are is the number of events that we've seen. The black crosses are our events. So this is the number that we've seen at this particular energy, and in this particular energy range here, the number that we've seen. So this is what this shows the evidence that we put in a paper to show that we've seen astrophysical neutrinos was this very graph here. And then underneath in these colours are the backgrounds, so those things that we also detect but are not what we want to see. And we can model those, and so this is what we can say would be the backgrounds here. So there's also those atmospheric neutrinos and those muons that are produced from the cosmic rays. And you can see that at these lower energies, what we are detecting is consistent with being background. But as you go out to higher energies, we're seeing more events that are above what we know the background looks like. So we can see from this shape, and we know the shape of this and what the backgrounds look like, so we can actually go over here to low energy where all our events are background and we know the shape, and then suddenly the shape changes and we see the astrophysical component coming in here. So this is the evidence that we showed to say that which is basically that we're seeing more at high energies than we would expect to see if it was just atmospheric neutrinos and these other backgrounds. So there's the evidence we showed that now we have seen astrophysical neutrinos. So we're very confident now that we have seen these astrophysical neutrinos. This is one of the highest energy events that we've seen, so one of the highest energy neutrinos. And we've seen now getting on for probably around close to 100, which we can say are astrophysical neutrinos. Trouble is that we can't actually tell where they're coming from. So you can definitely tell where they're coming from. They point back, but when we look in those directions, we don't see any particular astrophysical objects. So neutrinos definitely point back to their source, but remember they can come from the edge of the universe. So they can come from a very long way away that light itself can't get to us from. So far, when we look for where our neutrinos are coming from, we don't seem to see them correlated particularly with any astrophysical objects. Sometimes they do seem to be in the direction of an astrophysical object, but just about what you would expect by chance. If you picked a random direction in the sky, you can see an astrophysical object in that direction quite often. And the same with our neutrinos. If we take all of them as a set and look to see are there some astrophysical objects that line up with all of them, we haven't seen anything yet. So we're looking for more, because the more we have, the easier it will be to look for particular hotspots, and we might be able to see those correlations. But it suggests that they're probably quite faint sources, and we're just seeing one neutrino from each of those quite faint sources out there. It does suggest that they're definitely outside our galaxy that we're seeing from, but as I said, they could be very far away that light is not able to come from. But the great news is that we've seen the astrophysical neutrinos, but we're going to have to detect more, and we're going to have to study the ones that we've seen and study their energies to be able to tell more where they're coming from. Because basically we've got a new view of the universe, and it might be our only view of the high energy universe, because it might be the only messengers that we're getting from there. So it might be all those kind of suspect objects like the AGNs and the gamma ray bursts. It might not be any of them. It might be just something completely new that's where the cosmic rays are being produced, and neutrinos might be the only messenger that we'll be actually getting direct from those. So we're still going, we're still detecting, and we're still trying to learn more about those. So I'll try to give a talk in another few years where I'll tell you much more about those objects. This was to tell you that that we found the astrophysical objects, and they were opening this new window on the universe. So thank you very much.